Hi, my name is Beth Fawcett, and today I'm going to be sharing with you a presentation that I gave to the Fort Worth Gem and Mineral Club on August 24th, 2019. I was invited as a chemist to talk about something about chemistry that involved gems and minerals, and so naturally I had to talk about why gems and minerals are the color that they are. And to start off the evening, I shared a joke with my fellow mineral enthusiasts, and it starts off: I like rocks, and me and my friends look at rocks all the time, and sometimes the rocks are neat, and we tell our other friends about it, and our other friends also like rocks, and sometimes we have rock parties, and so now we know a lot about rocks. And that is how I feel about working with the people at the Gem and Mineral Club in Fort Worth. They are great. They know a lot about rocks, and they share what they know, and we're all really excited about it. And the life of a scientist sounds way more fun when you describe it like you're a 6-year-old. This is a comic from one of my favorite online comics. So let's get into why gem and minerals are the color that they are. So it starts off with a metal inclusion, or what can be viewed as an impurity in the stone. For instance, diamonds are only made of carbon. Diamonds are also completely clear. Now, whenever you get something in there that's not carbon, then you can end up with things that are colored. My favorite stone is a fire agate, so I'll be using it throughout the example that I'm sharing with you today. And this is what a raw fire agate looks like. It's got some chalcedony on top, and it's got some matrix here on the bottom. The fire agate is this brown, red, almost iridescent rainbow color. And what causes that is a metal inclusion. Now, on your periodic table, metals are going to be everything left, so everything over here, of this red line that you're seeing on your screen right now. And that's where we're going to be focusing our discussion today, is on these metals. Now, this is the chemical formula for fire agate. The silicon oxide is this clear chalcedony that you're seeing on top, and it has this inclusion of iron oxide. So once you've identified the metal that is associated with your stone, you're ready to figure out why your favorite stone is the color that it is. I have some common examples off here to the side: some garnet, some jade, topaz, turquoise, and each of them have a metal inclusion, and that metal inclusion is why that stone is the color that it is. Let's dive into it. So for fire agate, I'm going to be talking about iron. And iron is located in the center of the periodic table, and I've boxed it in for you today. Now, this might look like a lot. I'll explain what's happening. In this red section here, this is called the S block, and it represents a certain type of atomic structure. Over here on the right-hand side, we have what's known as the P block, and it's drawn up in green. Then we have in the center the D block, which is drawn up in blue. And then on the bottom, we have the F block, which is drawn in purple. Now, for your metal inclusion, once you've identified it on your periodic table, you need to actually draw in the quantum atomic structure. Now, what I mean by that is basically how are the electrons within your molecule aligning. And here you'll see I have an arrow, and it's pointing up. Then my number 2 over here is pointing down. Then I have 3 up, 4 down, and you're going to continue drawing your up and down arrows across your periodic table all the way up until you get to your metal inclusion. Now, once you get to that point, if you are left with an up that is not paired with a down, that's going to tell you something. This incomplete row here tells me something about the quantum state of this particular ion inclusion and how it interacts with other atoms and other molecules. So If I'm left with an unpaired arrow, for instance, if I were to use cobalt or copper or any other odd numbered atom on the periodic table, then that is the electron that I would address first. However, for iron, I'm on an even number and I have paired electrons. So instead, what I'm going to be doing is looking at this last incomplete line. And because the s orbital comes first, it is larger. And the reason why I know that, you see here it says d minus 1. These rows are numbered 1, 2, 3, 4, 5, 6, 7. And that kind of tells you a little bit about the size. The name of the block tells you about the shape. And here with D, I'm actually at D minus 1. So what that means is this row actually is at level 3. And this S block, which is level 4, is going to come first. So whenever iron interacts with the world, the first thing that happens is these two electrons on this s orbital are exposed for interaction. And whenever that happens, something called oxidation happens. So when I'm losing these electrons to another substance, like in this case, oxygen, something happens. And I want to get into what happens when those electrons are lost. I'd like to read to you today an excerpt from a paper that was published a very long time ago by Carl Darrow. And it reads, "Scattering of light is one of the commonest of all phenomena, which does not in the least imply that it is one of the most commonplace. Even its practical importance entitles it to high respect. We are often told that were it not for scattering, the sky would not be blue. The sun and the stars would not stand out amazingly brilliant against a background black as coal. It is probable, however, that if scattering were suddenly to be suspended, the disappearance of the sky would be one of the least of our worries. Everything else would disappear, except what was self-luminous. The visible world would consist of the sun, the other stars, and flames, and some electrical discharges in the filaments of incandescent lamps, and some substances glowing feebly with fluorescence or phosphorescence. Nothing else could be seen except as a silhouette, apart from objects so translucent that they could be viewed as a stereopticon slide against a flame. Happily, no calamity impends, and we may unconcernedly consider the theoretical importance, which is great. As some might say, the scattering of light is one of the backgrounds between the undulatory and the corpuscular theories. Metaphors of combat are, however, not appropriate. It is necessary to reconcile the theories, not to smash one or the other. Now it happens that some of the phenomena of scattering may be interpreted by one theory, and some by the other, and some can be explained by either, which is the most auspicious. For if this can some day be said of all of the phenomena of light, the goal of our desires will have been attained." The reason why I wanted to include this passage is because it explains what happens if light were to never scatter. If the sun shone down on the earth and that light was just absorbed or transmuted, we actually wouldn't be able to see anything except in a silhouette. Now, this quantum state creates an environment in which light scatters. And the different electrons that are associated, the different bonds that are in place, change how that light scatters. And this is based on something called an absorption spectrum. Now, these levels are something that happens. This is different than the rows in the periodic table that we were talking about. These levels occur whenever those electrons are lost to whatever your metal inclusion is being bound to. So the moment that that bond happens, those electrons get excited. They're excited to meet new people. They're excited to interact with other things. And that excitement after that bond is formed, results in an energy loss. And this energy loss can be seen on the visible spectrum. And that energy loss, again, is part of what creates the environment that causes the scattering of light. So what happens is, based on our S, P, D, and F orbitals, I mentioned that the SPDF, those names related to shapes, this is what the shapes look like. As you go down the periodic table, things increase in complexity. Things have more difficult time interacting with other things. And what happens is we have this thing called a photon. Now, a photon is a release of energy that may or may not be visible depending on the energy that it's at. Now, as our electrons from our metal inclusions are jumping up into higher energy states to interact with their surroundings, they can jump up from 1 to 2, they can jump up from 1 to 3, they can jump from 2 to 3. As you increase the number of orbits, as you move down the periodic table, things grow increasingly more complex. And you get a wave, ultimately, that's emitted. Now, that wave can be measured and can be seen. So the theory behind light waves and the Raman effect is what allows us to see this interaction, this chemical interaction here taking place. If you would like more information about the Raman effect and how it works, I have this linked in the presentation, and you'll be able to find that in the description of this video. So, because light waves are emitted and our eyes can perceive them and see them, I want to give you a little bit of an anatomy lesson about how the eye perceives color. Now, the most important, there's a lot going on in this image on the left. I'll get to the image on the right here in a little bit. But the most important part of this image on the left is this yellow. It almost looks like a border, but this yellow part is the optic nerve. And there's a particular part on this optic nerve where there's a gap. And that gap is called the foeva. The foeva is part of something called the macula. And the macula has the highest density of rods and cones in the eye. Now, rods and cones are the receptors. They receive the waves from the outside world through the lens. So the light waves travel into the eye and hit the retina. So the retina receives that signal. Basically what happens with the rods and the cones is as the wave hits them, they vibrate with a certain type of frequency. And the highest density of those are in this place called the macula. And then there's this special spot on the retina called the foeva. Now the foeva has 0 rods. And rods are what allows us to perceive black and white. Cones are what allow us to see color. So at the foeva, there are 0 rods and there are a significant amount of cones. So if you're vibrating a lot of the cones at the foeva, then that is kind of like a really intense color. And depending on how fast that wave is moving, how intense the wave is, it'll move to a different spot on the color spectrum. Waves that are moving faster are going to be closer to purple. Waves that are a lot slower are going to be at red. And so the speed of the vibration that happens at the cones will give us not only the perception of purple to red, but will also give us the perception of that in color intensity based on the number of inputs that we're receiving. And so this graph kind of shows you, in general, for a human, the angle, so the distance from the foeva, and how many receptors there are at those distances. The highest density of cones, of course, is going to be right on top of the foeva. The blind spot is where the optic nerve moves into the eye. There are no rods or cones there. So each gemstone has a different metal inclusion. That metal inclusion, based on its interaction with the other things that are present in each chemical makeup of each mineral, gives off a different type of energy. And that different energy is what allows us to see color. So, to conclude, the reason why gemstones are the color that they are is because of the metal inclusion that's present there. Now, what this means for you as a rock hunter is that if you can find where there is something like a copper mine, and copper is either blue or green, if you can find the location of a copper mine, that means you'll be able to find stones that have that copper inclusion nearby. That's why turquoise is so prevalent in Arizona, and why agate and jasper is so common in Texas. There's a lot of iron in the ground here. So that can empower your gemstone hunting activities, is by looking at where various metals are mined around the world. Thank you for watching my presentation today. If you have any questions, I will leave my contact information in the description of this video. Thank you so much. Have a great day.